I have a question for you. You mentioned that your sculpture wouldn't be the same with nylon wire.
Mon anglais
Oui,
est
oui, oui.
pas trop.
Donc, vous avez dit que les sculptures seraient pas les mêmes s'il y avait un fil de nylon qui les
Oui,
tenait par
oui,
rapport. Donc, l'élasticité, elle est dans.
dans la matière.
Et si je mettais un élastique, par exemple.
Eh ben, essayez.
C'est-
Non, c'est vraiment une particularité de découvrir avec un physicien des propriétés et de réfléchir pendant 16 ans à la manière la plus pertinente d'utiliser ces propriétés. Et les propriétés des mémoires de forme ont trois possibilités. Il y a la mémoire de forme qui est vraiment vous éduquer une forme à une température avec une contrainte mécanique et thermique. Ensuite, vous pouvez faire cette même chose pour créer une superélasticité qui est 8% au-delà de la normale. Si on prend des monocristallins, ça peut aller jusqu'à 16%, ce qui est énorme. Et puis, vous pouvez faire un nœud, le défaire, et il n'y a aucune trace dans le métal qui est imprimée, qui reste en mémoire. Donc, c'est assez fascinant. Et le troisième, c'est fort amortissement, qui est des propriétés qu'on peut utiliser. Par exemple, une cloche, la forme d'une cloche, elle ne sonne pas. Vous la trempez dans l'eau chaude et elle résonne. Voilà, c'est des possibilités qu'on utilise pour... alors, les mémoires de forme, je fais juste une parenthèse. L'utilisation la plus courante actuellement, c'est les stents, qui sont très, très, très présentes dans la vie de tous les jours. Et ça, c'est des matériaux qui ont justement cette capacité de se rétracter, par exemple, et à température X, ils reprennent leur forme, qui est par exemple un ressort très très ouvert qui permet d'avoir la résistance. Alors, essayez avec du nylon de tisser un petit tuyau en fil, vous le comprimez, il ne reviendra pas. Et en métal ressort, il sera très ressort, mais vous ne pourrez pas le contracter pour l'enfiler pour une application médicale, par exemple. Voilà.
It's interesting because Nengudi, the artwork I show you on the second images, she worked with tide, so it's like nylon. It's also nylon, and she used this material to say, okay, if I take the tide and tirer, stretch, or stretch it very very hard, it will not come back exactly the same way it used to be. So it's really like if you stretch a body into a society with bad behavior, it was really about the rights of the black people in United States. If you binding and stretch a body into something bad, into I don't have the words, but into bad behavior, it will not come back exactly. It will be, distorted. Yeah. So it's really interesting because here the material speak with something, speak with a message, speak with a concept. Different way, but.
Okay, thank you. Maybe I will ask a question to all the panelists, or you will decide. So maybe part for you, Louis, but for everybody else. Actually, also, in my presentation, I forgot to show you 3 or 4 more slides, which were just picture, and some of them by Escher and some other. And but it's too bad, and I don't want to take a few minutes now to restore it. Some of them were were spheres from sculpture, but this is easy to figure out. You just Google image sphere and in sculpture, and you will see such a vast choice of beautiful spheres that creator visual artists actually create. And there is no doubt that, I mean, not only Google, but when you see this, and like the sphere of Etienne there, you see, and what is this, you ask? And you say it's a sphere. Now we're a mathematician and we like definition, and you look at the definition of a sphere, and it's not a sphere, of course, because we have a certain definition and it doesn't follow the definition. So that's why actually I think the idea of archetype is interesting, because, okay, they are not sphere, but they're almost sphere. I mean, in Hugo, he mentioned several times in this interaction with journalists recently, that in mathematics we are sometimes interested in what does it mean for two shapes to be close, to be nearby. Okay, so okay, there are things that are not exactly sphere in a mathematical sense, and everybody will call them spheres in some context, except if we want to trick you and you say, well, it's not a sphere, so we are not going to call it a sphere. So here, I think the first presentation by Indira, she also presented you something like, okay, I'm going to decide that we will change metric, and with this new metric, this is going to be a sphere. And doing that, I can do strange things like tiling a plane with spheres or balls. So maybe for Louis, but I'd like to hear you whether this is actually a relevant idea of archetype, that there is something that you identify a sphere, even if it's not the juridical, the technical, the mathematical definition of a sphere. And so, in some sense, in linguistics, it's interesting because how do we agree? How do we understand each other? By using a word, like the word blue or whatever, when actually it does not match the definition that everybody will think. So it's exactly, I think, maybe a question for several of you. I don't know who wants to say something.
So very quickly, I think, well, linguistics is about natural language use, and the fact, the cognitive fact, is that we don't use much definitions in our ordinary lives. So we don't access any kind of definition. So we need to have something much more efficient in mutual understanding than searching for definitions. We don't have an internal dictionary in the form of a dictionary that we see in libraries or on internet. We've got something different. And one assumption, which is quite common now in linguistics, is that what we have actually is precisely patterns of reference. That's the way we acquire the meaning of words. That's been shown in psychology very clearly. So we acquire the notion of whatever by matching shapes. That's the first way we go. And then we'll have a Bayesian statistics that works and identifies central patterns or prototypes. And this works very well with the philosophy of Wittgenstein, who's theorized this idea early on by considering the meaning of words. And his example is the word game. It's a very classical example. It means that there is no possible definition for that word. And so the fact is that we just activate, depending on the context of use, certain particular properties that raise a sort of a prototype, and we see if what we are talking about resembles that prototype to a certain extent. And that's much quicker in mutual understanding. Of course, it creates the space for misunderstanding. Misunderstandings would not occur if we had in our mind proper dictionaries and encyclopedias. We don't have that. We are much quicker because we need that to survive and go quicker in life. And the same goes with our reasonings and the way speeches are constructed and understood. So we have those spontaneous inferences that we draw all the time. There's a lot of meaning which is implicit, not being said explicitly. We cannot spend, it's impossible actually to spell out everything we want to say, to be as precise as being fully explicit. That does not exist. language is vastly ambiguous, and so the brain does the rest. Sorry.
Yes, okay, so I think one thing is that it's true that in mathematics or in science in general, I mean, we need very precise definitions of things. And I think in art, actually one benefits from not having such a precise definition, or maybe using more a list of properties which is more open to judgment and interpretation. And I think that's actually an illustration of some of the things I was trying to say before, because despite the fact that one can change the metric of a sphere and so they look different, in mathematics, a sphere somehow really is always a sphere. It's a very tight definition. And despite the changes you might get from changing the metric, it's always a sphere. And it has to be, because we need that very, very precise definition. Whereas in art, you use that space, you use the fact that there are different interpretations, different contexts, to add something, to create the meaning. So I see that as a different thing. Another thing to say on a different point is that just what you were saying before, Mark, about the idea of the mathematical sphere, and they're not, I mean, that's a very idealized sphere. It's really very, very true, because in mathematics, you have a definition of a sphere. It's idealized. It's an object which has this perfect symmetry. But if you actually try and see a sphere, you can't see a perfect sphere. You're forced to, for example, break that perfect symmetry if you want to see it. You need, for example, a light. And a light will mean that you have shadow, which means that you will have some preferred point or some preferred perspective on it. You could respond by saying, let's try and make uniform light. But actually, if you look at an actual sphere with uniform light, you won't see a sphere, you'll see a disk. So in fact, you really need to have, if you want to think of a genuinely perfect sphere, it really only exists in the mathematical sense. And its instances, its physical instances, will actually not be the same thing as we have in mathematics.
Okay, thank you. Maybe I suggest the public, it means you, want to comment, intervene, ask question, object. There is no rule, so except you need the mic. That's the only rule.
Yeah, thank you for all these very nice presentations. So I want to ask a question about, well, to every one of you, but it's about Paul's presentation about archetypes. So going from universal archetype to the example archetypes. So it seems very difficult to go from universal to the example, in particular if you take like a mathematical concept. And you may think, okay, so let's take the average or an average notion of the archetype to create an instance or an example of the archetype. But usually it's very bad. It doesn't give you what you will perceive as an archetype of your universal archetype. So is there any example, or is there any, maybe can you comment on these difficulties to go from universal, and I ask every one of you, of course, to the example?
Yeah, okay, so I guess the way I see this is that if you have some kind of universal archetype in the type that in the sense that I was talking about, then Mark used the word prototype, and close to prototype is perhaps stereotype as well. And I think one of the roles of art, at least, is to actually break with the archetype. And that's where the interest is. And this is very much actually fits in with what Valerie was saying. If you take the concept of a bed, for example, as your universal thing, if you were to represent or draw a sort of average bed, that wouldn't, I mean, it might be worthwhile doing, but it's not perhaps so interesting from an artistic point of view. What's interesting is, and this is why, as Valerie explained, why Tracy Emin's bed is interesting, is because you ask the where, the why. You find a context for it, which is rather different, which breaks perhaps with the perceived idea or maybe the stereotypical idea that we have of that particular concept. I don't know if anyone else wants to weigh in on that.
I saw a hand there.
Thanks.
Thank you very much for this very nice, wonderful, inspiring tour d'horizon, starting from balls and spheres, going to shape memory, then further iconography and archetyping in painting and linguistics. My question is about whether you might help me understanding the tremendous gap Marina Vyazovska made, going from 3 dimensions to 8 dimensions and even 24th. I tried to imagine maybe there was curved space involved, but as Indira Chattery announced, there was maybe there was definitely more than a taxilab metric. But when I recur to the paper of Marina Vyazovska, her entire derivation was made in the framework of Euclidean geometry. So there is no unusual geometry. Still, she managed to go from 3 to 8 dimensions and even 24. How could you, a simple molecular scientist, maybe illuminate how she could have made this gap?
Maybe I will very quickly answer, because this is impossible to really summarize this. But it's not exactly true that there is no non-Euclidean geometry in the work of Marina Vyazovska, because she used a theory inspired or related to her research in arithmetic and number theory. And the theory is called modular forms, and the theory of modular form is actually related to 2-dimensional hyperbolic geometry, which we have mentioned here and there. And that's one of the things about mathematics, is that very often you have a very hidden and very deep connection between 2 different theories. And so this is like a leverage that she has been using to explore these very specific structure in dimension 8 and 24. Unfortunately, don't count on me to define what is a modular form, but that could be for another interesting discussion. But thank you for the question. Maybe.
Yes, I saw this coming my way. Well, firstly, is this premise true? Is it true that they're less well understood? I mean, I think that yes, they're different, and you ask different questions about both different situations, about the two situations. I think perhaps one answer to this would be to say that, let me just maybe talk about sort of art and then maybe math again. So in art, I think you start from something tangible and you go towards something intangible. But the thing you start from, in some sense, may be easier in the sense that you have these examples, which is what you're saying. So the starting point is that, but you end up somewhere difficult, you end up somewhere more intangible. And perhaps in math, or in science in general, it's a little bit the other way. You start with something which is completely intangible, and the role is to maybe make that a little bit more tangible. I'd be very happy for anyone to either contradict me or say something that adds to that. But there might be something true about what I just said.
Well, you know this idea about classical geometry, that classical geometry and Euclid geometry, theorem about triangle, is the art of correctly reasoning on false figures. Maybe very quickly one last question, because one of the archetypes is time going on, and I have two raising hands. But
so I find also, as a previous question, I found this distinction between universal archetypes and examples very thought-provoking. Although, yeah, I'm not like you gave this distinction between art and math, as art dealing with examples rather than math dealing with universal archetypes. As a mathematician, in my experience, I start with something tangible, and then I try to go to more abstraction to get a sense of it. Let's take the example of the square root of 2, right? Irrational numbers were discovered by one concrete example that was shown to be irrational. So like the universal archetype was discovered by the first meeting of this example, concrete example. So I would say that history of mathematics maybe can help us to understand, do Grothendieck's works, for example, come from somewhere, from the abstract Platonic world, or he did start with some basic, I don't know, algebraic surfaces before doing his big theory. So, and the question more for the practice, for the art practice and mathematical practice, like, I think it's a very interesting way of reading the mathematical and artistic practice, but maybe each artist and each mathematician can say how they perceive this. Maybe for the artist, like does the work with metal, for example, can it be interpreted as a pushing to the universal archetype through a concrete material rather than creating a particular example of an archetype, right? I don't know how the artist thinks, but I think I make a conjecture that maybe different artists search in different ways and in this archetypal world. So maybe you can react.
No, I want to be the villain now. Because we really have to respect the time. So we will stop here. Maybe some of the questions will reappear in some of the next panel, and everybody here has a chance to think about how archetype will help them boost their creativity and research. Thank you very much to everybody and to the public.